Hello, class. In this section, you're going to learn 3 kinematic equations. Remember, kinematic just means motion. So you're going to learn the equations that describe motion. Now, before we begin, there are 3 main assumptions we are going to make when using these equations. The first and most important assumption to remember is that we assume acceleration is constant. That means the acceleration will stay the same value during a problem we're examining. The second assumption is that the initial time starts at 0 seconds. And the third assumption is that gravity is constant at 9.8 meters per second squared. We're going to start off with the simplest derivation for our first kinematic equation. Recall that acceleration equals the change of velocity over the change of time. Now, instead of writing subs of f for final and subs of I for initial, we're going to write subs of naught, which is that little 0 you see, to represent the initial point, and then no subscript to represent the final point. Now, according to our first assumption, we assume that the initial time is 0. So now our acceleration equation is simplified. The last step is to solve for velocity. And there you have it, our first kinematic equation. You do not need to know how to derive this equation. Just write down the equation in the red box. To start with deriving our second kinematic equation, we're going to begin with the definition for average velocity, which is the change of position over the change of time. Again, recall that the initial time is 0. Then rearrange the equation to solve for x. However, we cannot stop here because unlike acceleration, we do not assume that the velocity is constant throughout the object's entire motion. So we must make a substitution with the average velocity definition of v naught plus v over 2. With the help of some algebra, we get the final equation of x equals x naught plus vx naught t plus 1/2 at squared. Again, don't worry about the derivation. Just write down the equation in the red box. The last kinematic equation is found by combining the previous equations to eliminate time. We won't go through this derivation, but make sure you write down the last kinematic equation. Below you see the 4 equations. I don't count equation 211d as part of the kinematic equation group, but the other 3 are the main kinematic equations you'll use to solve motion problems. You do not need to memorize these equations. However, you do need to write these equations down and have easy access to use them for solving motion problems. Here are 9 recommended steps to solve problems. Read the whole problem or story and make sure you understand it. Underline any key words. Then draw a diagram and a coordinate axis if you need to. Step 3, write down the knowns, which are given quantities, and then the unknowns, which are the ones that you need to find. Step 4, which equation relates to the known, which are the given quantities, and the unknowns, which are the ones you're trying to find. Step 5, solve algebraically for the unknown quantities. Then step 6, use your calculator and plug and chug. Can you use your calculator? And then step 7, just check your units. Make sure your units make sense. Alright, now let's do an example of an airplane motion. The 2 pictures you see are Cessna 172 aircrafts at my undergraduate university. The school is connected to Daytona Beach Airport for teaching students to fly and be an air traffic controller or other aviation studies. Now let's say you're designing an airport for small planes. One kind of airplane that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second and can accelerate at 2 meters per second squared. Part A asks if the runway is 150 meters long, can this airplane reach the required speed for takeoff? And then Part B states, if not, what minimum length must the runway have? The first step is to write out your givens. We're given the final velocity to be 27.8 meters per second. We assume the initial velocity is 0, starting from rest. The acceleration is given at 2 meters per second squared. The final position is 150, and therefore we'll assume the initial position is 0. The velocity is highlighted in purple because we're solving for velocity to see if it's equal or greater than 27.8 meters per second. If the velocity we find is less, then the runway must be longer for the airplane to gain enough speed for takeoff. The second step is to write down what you're finding, which is the final velocity. The third step is to look at your 3 kinematic equations to determine which one has the variable you're looking for, which is final velocity, and the variables you're given. In this problem, v squared equals v naught squared plus 2a times x minus x naught is the perfect match, since the other 2 equations have time and we don't know what time is. Now, the fourth step is to cross out any variables that equal 0. So in this case, we have v naught and x naught. Now we can simplify this equation to get v squared equals 2ax. Now we need to solve for v, which equals the square root of 2ax. Next, we plug and chug, and we'll get 24 meters per second as your final velocity. Notice how the square root also cancels out the square and the units so that we have the correct unit for velocity, which is meters per second. Can this airplane reach the required speed for takeoff? No, because 24.5 meters per second is less than 27.8 meters per second, so the runway needs to be a little bit longer. Now for part B, it states, if not, what minimum length must the runway have? We have the same variables, but this time we're solving for x, the final position, or how long the runway must be. Which equation do you think best fits this scenario? Correct, the same kinematic equation we used last time, but instead we're solving for the final position, variable x. Cross out any variables that are 0, and the equation reduces down to v squared, which equals 2ax. But now we're solving for x, so rearrange this equation to get v squared over 2a. Then plug and chug to get 193 meters. So the runway must be at least 193 meters for this small airplane to have enough speed for takeoff. Again, take a look at how the units cancel out so that we're just left with meters. Exercise D. A car starts from rest and accelerates at a constant 10 meters per second squared during a 402 meter race. How fast is the car going at the finish line? First step, write out your givens. It starts from rest, so the initial velocity is 0. We're given that the acceleration is 10 meters per second squared. The final position is 402, so we'll assume the initial position is 0. We're trying to find the variable v, the final velocity at the finish line. And now take a look at your 3 kinematic equations. Which one do you think would work for solving for the final velocity, which is variable v? That's correct, the same equation we used in the last example. Now cancel out any variables that are 0, which is v naught and x naught, then rearrange the equation to get v squared, which equals 2ax, and therefore velocity equals the square root of 2ax. Plug and chug, and we get 90 meters per second. Next example. How long does it take for a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second squared? First step, write out your givens. The final position is 30 meters. We'll assume the initial position is 0. It starts from rest, so the initial velocity is 0, and we're given that the acceleration is 2 meters per second. And what we're trying to find is how long, which is the variable t, for time. Can you guess which of the three kinematic equations we should use? Correct. X equals x naught plus vx naught t plus 1/2 at squared. Now, cross out any variables that equal 0. Then rearrange the equation to get x equals 1/2 at squared. Now rearrange the equation so that we can solve for time, which equals the square root of 2x over a. Then, just plug and chug, calculate your answer to get 5.48 seconds. So it takes the car almost 5.5 seconds to cross a 30-meter intersection with an acceleration of 2 meters per second squared if it starts from rest.